Welcome back to another online instructional lesson for Algebra 2. If you remember, we have been focused on sequences and series in this unit, specifically leaving off with arithmetic sequences. Today, our focus is going to turn to geometric sequences. So we are going to define and dive into a little bit deeper into what geometric sequences are and their purposes. Remember, you can find these notes on Google Classroom if you have the ability to print. If not, make sure that you are taking notes following along with a piece of notebook paper so that you have it available to use on your assessment. Let's start with a definition for a geometric sequence. So this may be a term that you are familiar with. You may have heard it and probably heard it and worked with it in Algebra 1. But a geometric sequence is a sequence created by multiplying the same value, which is known as a common ratio, to successive terms in a list. So you start with the first term and you multiply a number to that, and that gives you the second term. And then you multiply a number to that, and that gives you a third term, and so on and so forth. So you'll notice that this is very similar to arithmetic sequences, where we started with a term and we had a common number that we added to each term as we went along. This time, it's going to be a little bit different. We're multiplying. So let's, for example, let's say we start with the number 1, and we multiply this number by 2. So the next number in the list would be 2. Then we would take 2 and multiply it by 2. Our next number would be 4. And then we'd multiply that number by 2, and the next number would be 8, and then 16, and then 32, and then we could continue doing this forever. This would be a geometric sequence. So if I took the method of finding out if it's arithmetic, we'll notice that the difference between the first is a positive 1. And then the difference is 2, and the difference is 4, and then the difference is 8, and the difference is 16. So we may notice here that this difference is doubling every time along the way. So if we want to figure out if something is a geometric sequence, like in problem number 1, basically what we want to figure out is what is this common ratio, which we usually denote with an R. So similar to arithmetic sequences, what we can do is we can take a look at the terms in the list. And we can do a little bit of computation to figure out what the ratio is in between these. So previously, with arithmetic sequences, we picked a term and then we subtracted the number before. Now, because this is multiplication and division, what we're going to do instead is we're going to pick a term and then divide the number that came before. So if you can see this without typing it into your calculator, that's okay. So if you can see this goes from 1 to 1/2 to 1/4 to 1/8, you can figure out that pattern. Perfect. You can go with that. But if not, we can take this 0.5 and divide by 1. And so I'm going to go ahead and put this in a fraction. We're going to work primarily with fractions here. So it is a 1/2 multiplication between 1 and 0.5, or 1/2. And then do it for the next two terms. So 0.25 divided by, 0.25 divided by 0.5. And this would also be 0.5, or 1/2. Then I could do it again. So 0.125 divided by oh, sorry, divided by 0.25. And we'd see that it's another 1/2. So yes, this is a geometric sequence. And we would say that if we were asked, we would say that the ratio is 1/2 or 0.5. Again, primarily I'll write fractions, but if you write decimals, that's okay. So the ratio, as we multiply each term, we multiply each term by 1/2 or 0.5 to figure out what the next term was. So if we did this as fractions, this would be 1, 1/2, 1/4, 1/8, and it'd be easier for us to see this pattern here in fractions. We'd see the next one's 1/16, 1/32, and so on and so forth. Go ahead and take a look at B. In B, this is fractions. This one's written as fractions and not decimals, so we may not need the calculator here. So I could take a look at the 1/4 and the 1/8. What multiplies to 1/8 to give me 1/4? If you said 2, that would be correct. You could also find that by, in your calculator, taking 1/4 and dividing by, and being careful here to put 1/8 in parentheses. If you have an older calculator, you'd see that it's 2. Now, what would multiply to 1/4 to give me 3/4? If you said 3, then you'd be correct. So again, in the calculator, this would be 3/4 divided by 1/4, putting the 1/4, the denominator in parentheses here, would be 3. So we can see here that this is not a geometric sequence. We could carry this on and find out that the multiplier between 3/4 and 3 would be 4, and then the multiplier here would be 5. So we could probably see the pattern. We'd multiply 15 by 6 and that number by 7. We can see that pattern emerging here, but we may notice that this is not a consistent number, so this is not a geometric sequence. So like an arithmetic sequence, we're looking for the multiplier in between these, and it has to be the same to be a geometric sequence. So similar process, but again, we are dividing the terms. We're finding what is being multiplied as opposed to in arithmetic sequences when we subtracted or finded what was being added. See if you can pause the video and determine if C is a geometric sequence. So go ahead and pause now. Hopefully you had enough time to figure out that C is, in fact, a geometric sequence. So if we took a look here, we may notice that from positive 128 to negative 132, that was a common ratio of negative 1/4. So if I take 128 and multiply by negative 1/4, or negative 0.25, that would give me negative 32. If I took negative 32 and multiplied by another negative 1/4, that would give me positive 8, or multiplied by negative 0.25. Did the same thing from 8 to negative 2 and find out that it's 1/4. So again, you can find these by taking a number, so let's say negative 2, and dividing by the previous number, 8. And that would be negative 0.25, which is also negative 1/4. So we would say, yes, this is a geometric sequence, and the ratio in this case would be negative 1/4. So similar to arithmetic sequences, but instead of adding and subtracting, we're working with multiplication and dividing. So in problem number 2, it asks us to find the first 5 terms for the sequence with the given information. So it gives us the first term, and it gives us a ratio. So again, we need to find this list. The first term in the list is going to be the first term that they give us, negative 1, or negative 16. Now, how we can get the rest of these is by multiplying by the ratio. So this ratio is 0.25, which is also 1/4. So what I'm going to do here is I'm going to take negative 16 and multiply by 0.25. If you divide it by 4, that would be the same thing. That's going to give me negative 4. Then I'm going to repeat this process. Multiply by 0.25 or divide by 4 and be the same concept. And get the next term in the list. And then repeat, multiply by 0.25 or divide by negative, or sorry, divide by 4, and this would be negative 0.25, which is negative 1/4. You can also find that by hitting math fraction. And then again, one more time, multiply by 0.25, which would be dividing by 4, which would give you negative 1/16. So the first 5 terms in this list would be negative 16, negative 4, and negative 1, negative 1/4, and negative 16, found by taking the previous term and multiplying by 0.25 or dividing by 4. Now, see if you can pause the video and figure the first 5 terms in this sequence denoted in B. Hopefully you had a chance there to get an answer. So the first 5 terms, this is going to start with, oops, sorry here, this is going to start with 2/3. And if I multiply by 1/5, this would become 2/15. It's probably easiest to take a look at these as fractions and multiplying, sorry, a negative 1/5. Sorry, multiplying by a negative 1/5 would change it to negative 2/15. It's probably easiest to take a look at these as fractions because all you have to do is multiply the denominator by 5 and the numerator by 1. So this would be negative 2/15. If you did this in the calculator, 2/3 times negative 1/5, and this would give you a decimal, which you could hit math fraction, put it into a fraction, so we don't have to round or worry about repeating decimals. Then, if I repeat this process, negative 2 times, so times negative 1/5, put that into a fraction, this would give me positive 2 over 75. And we can repeat this process. So the next one would be a negative 2 over 375. And finally, the fifth one in the list would be positive 2 over 1875. So notice here, because the ratio is a negative number, that it changes the sign in as we move through successive terms in the list. Again, it's probably easier to multiply these as fractions, but you can always do them in calculator as decimals and then convert to fractions, so we don't have to worry about big decimals like 2 over 1875. Kind of a long string to write out, so maybe fractions is better here. Okay, so we can find the terms in the list by taking the first term and multiplying by the ratio. Now, things, when the number of terms is short, that's not bad. So if we had to find the fifth term, if we had to find the fifth term in a list, we could do this process until we got to term number 5 and say, oh, I see. The fifth term is 2 over 1875. But if it asks us to find the 30th term, this would get pretty tedious because we've done this through 5 terms, but we'd have to keep doing it and keep doing it and keep doing it and keep track of all of our work until we get to 30. Or, like with arithmetic sequences, we're going to find that we have a shortcut. And this shortcut can be used through, or can be found through a formula. So we had an nth term for an arithmetic sequence formula. Now we have an nth term for a geometric sequence formula. This term is, or this equation uses the same concepts, but is built a little bit differently. Again, we're not going to go through the proof of this on this video, but if you're interested, let me know and I can walk you through it. So this is telling us a sub n here again is any term in the list. A sub 1 is the first term. R is the common ratio. So this is the number that's being multiplied to each term to get the next term. And then n is the number of terms that we're on. So if, let's say, we want to find the 20th term, a sub 20 would be our a sub n that we're looking for, and n would be 20. So for problem number 3, it says find the 10th term of the sequence. So one way we could take a look at problem number 10 is to find the common ratio. So if you found the common ratio, if you look at this and you find the common ratio, we notice that the sign is switching, so the common ratio has to be negative, and hopefully we could see that it's a negative 2 that's being multiplied in each one of these cases. So the common ratio, common ratio is going to be negative 2. So what we could do is take this fourth term and multiply by negative 2, and then take that fifth term and multiply by negative 2. And do that 10 times to get to the 10th term. Or we could use this formula where we already know that r is negative 2. So if we want to find a sub 10, the 10th term, the value of the 10th term in the list, we can use the first term, a sub 1, which is 3, times our ratio, which is negative 2, to the n minus 1 power. So to the 10 minus 1 power. So if we simplify this, this would be 3 times negative 2 to the 9th power. And that we can evaluate in the calculator. So we can, if we use this formula and substitute correctly, we only have to do one step in the calculator this time. So we can type in this expression, and this would tell us that the 10th term is negative 1,536. So this would be equivalent to, again, let's go through this the longer way. Let's say take negative 24 times negative 2. That's the fifth, sorry. Yes, so that's the fifth term times negative 2. That's the sixth term times negative 2. That's the seventh term times negative 2. That's the eighth term times negative 2. That's the ninth term times negative 2. And there's our 10th term. So these two match up. This is just a little bit shorter calculation for finding the 10th term. Now, if the term's smaller, maybe you do go through the process of finding all the terms. But if the term, again, is like the 90th term in the list, you're definitely not going to want to do this 90 times to get to that 90th term. So we want to be able to use the equation there. Go ahead and pause the video and see if you can use the equation or the formula to find the 8th term for the sequence that's listed in problem number 4. Okay, so hopefully you noticed that And again, we have to find the common ratio here. So we want to make sure this is geometric first. So hopefully you notice that we're dividing by 5 from one term to the next, or it's 1/5 from one term to the next. So my r is going to be 1/5. Remember, dividing is the same as multiplying by the fraction here. So if I want to find the eighth term, that would be a sub 8. I need the first term, which is 625, times the ratio, which is 1/5, the common ratio, to the n minus 1 power. And so this would be the 8 minus 1 power if I'm trying to find the eighth term. So this would be 625 to the 1/5, or sorry, times 1/5 to the 7th power. And if you put that as a decimal, that would be 0.2, which is definitely okay to use. So 625 times 1/5 to the 7th power, or 0.2 to the 7th power, and you'd find a decimal answer of 0.0068, or if we did this as a fraction answer of 1 over 125. So either in this case would be okay. The decimal is not that long to write out, 0.008, but either of these two would be acceptable. So here we have an example, or examples of how to use the nth term formula to find the value of any given term in a geometric sequence. Now we can also use that formula to find how many terms are in a geometric sequence. So in problem number 5, we have this geometric sequence that starts at 4, it goes to 2, it goes to 1, and it goes on and on. So what we may notice here is, we could find this arithmetic-wise, but you may notice that this ratio is 1/2. So each time we're cutting that number in 1/2. So we know here, based on these, r equals 1/2. Now we want to find the number of terms. So in the previous two problems, they told us how many terms we were looking for, the 10th term and the 8th term. Here they give us the first 3 terms and then another term in the list, and then they leave out some terms. We want to figure out which number is 1 over 64. So what we can do is we can take the value of this term and put it in for a sub n. So 1 over 64 equals a sub 1. We do know that value is 4. We do know the ratio is 1/2, and we do know, or what we don't know here is n. We don't know the number of terms. So we want to be able to solve this for n. The first thing that we want to do, again, we have to get n by itself, is we want to get rid of this coefficient. So divide both sides by 4. So in my calculator, I'll take 1 over 64 and divide that by 4, and it's going to give me a decimal, but I'm going to go ahead and put that into a fraction. So that's 1 over 256 equals 1/2 to the n minus 1 power. So first thing here is that we get rid of that 4. Now we have to get n minus 1 out of the exponent. So this takes us back a couple units here. Remember, if we're solving an exponential equation, this is an exponential equation. It's exponential because the variable is in the exponent. We have to use a logarithmic equation. So the base of this exponential equation is 1/2. So what I need to do here is take the log with the same base, so log base 1/2 of both sides. So it's been a while since we've done this, but let me get the notation here correctly. I'm using the inverse operation of an exponential base, or an exponential equation with base 1/2. That would be a logarithmic equation with base 1/2. So what happens is the logarithmic equation and the exponential equation, these two right here, essentially undo each other's operation. So the left side of the equation, I'm going to start a new line, but the left side of the equation stays the same. Log base 1/2 of 1 over 256. The right side of the equation gets rid of the exponential base, and now I'm left with just n minus 1. So if you don't remember that, go ahead and take a look back in the notes sections. They're still on Google Classroom, and you can see a review how to do that. But if we need to solve for an exponent, we can use a logarithm that has the same base as the exponential expression. So now I have n minus 1 off by itself, so I can add 1 to both sides. So what I get is log, log base 1 half of 1 over 256 plus 1 equals n. And this is something that I can solve for using the calculator. Now, maybe in this case you don't have to solve using the calculator. Maybe you could do this arithmetic-wise, but remember we have the change. If you have the change of base button in your calculator, you can use that. The button that allows you to use a base other than 10. But if you don't, remember you can take log of the input, 1 over 256, divided by log of the base, 1 half. And now I have this expression right here. Don't forget to add 1 to this. And there we have the value for n. So there would be 9 total terms in this expression to get us to 1 over 64. And we could check this in this one. So let's leave off at 1. So 1 divided by 2, that's the fourth, the fifth, the sixth, the seventh, the eighth, and the ninth. And if I put that into a fraction, that is 1 over 64. So it is 9 total terms to get to 1 over 64. To solve that using the equation, we'd use this nth term equation, substitute into it, and then use the logarithms, or maybe even a change of base here. You could use the mutually exclusive base formula here if you wanted to as well, to get n by itself, and then use your calculator to evaluate. In number 6, we have something, a different way to use the nth term formula. In number 6, we saw these in arithmetic sequences, but it says find the first term and the common ratio of a geometric sequence where the fourth term is 0.075 and the seventh term is 0.009375. So that's what this means. A sub 4 is 0.0075, or 0.075 means that the fourth term is 0.075. So we need to find the first term, which is a sub 1, and the common ratio, which is r. It doesn't tell us either of those. But what we can do is take the information that we know and substitute it into this formula. So a sub 4 is 0.075. So for a fourth term, a sub n is 0.075. We don't know what a sub 1 is, so I'm just going to leave it as a sub 1. We don't know what r is, so I'm just going to leave it at r. For the fourth term, n is 4. So that means my exponent now is 4 minus 1, which is 3. So this gives me an equation. This equation is 0.075 is equal to a sub 1 times r to the third power. Now, this equation does not allow me to solve for a or r. Sorry, I'm going to move this down a little bit. It gives me two variables, so I cannot solve for either a or r. What I can do is create a second equation using this information. So for the seventh term, the value of the term is 0.009375. The first term is still unknown. And now the ratio is still unknown. But the exponent now for the seventh term would be 7 minus 1, which is 6. So this gives us a system of equations that we can solve or use to solve for either a sub 1 or r. Different ways that you could do it. But one way we could do, or one thing that we could do here, is divide the two equations. So if I divide the two equations, I'm going to divide the numbers in my calculator. So 0.009375. We talked about subtracting equations in the last topic, and that's the same as dividing the equations. I'm going to put this into a fraction. That's the same as dividing the equations, where we basically combine or divide the common terms. So let me actually just rewrite the way that it's represented. Rewrite it like this. So I'm going to divide the constants here. That would be 1/8. Now, the reason I'm going to divide these two equations is because if I divide a sub 1 by a sub 1, they're the same variable, so anything divided by itself is just 1. So basically there's a 1 here. And then r to the 6th power divided by r to the 3rd power. Remember, if we're dividing two exponents, or two expressions with their exponents, we subtract. So r to the 6th minus r to the 3rd is just r to the 3rd. So on the right side, this turns into r to the 3rd power. So the a sub 1's cancel each other out or divide out to give you 1, and now the r to the 3rd power, or the r to the 6th and r to the 3rd simplify to give us 1/8. Now the reason I wrote this as a fraction is because now it's easier to solve for r. We can take the cubed root of both sides. And again, this isn't the only way to solve the system of equations, but it's a way. So the cube root of 1/8 then would be like cube rooting 1. So the cube root of 1 is 1. The cube root of 8 is 2. So r is 1/2. And you could also do this in the calculator as well. This is a pretty quick computation mentally, but if you needed the calculator, hit the math key, go down to option number 4, that's the cube root, and then I could type in 1/8, and it's going to give me 0.5, which you could also write as your ratio. So r is 1/2 or 0.5. So we were able to find the common ratio by substituting in each of these values for the nth term equation, and that created a system of equations we could solve. Now I can go back and substitute this in to solve for a sub 1. So if I do that here, I'm going to take this and substitute it back in there. It's going to give me 0.075 equals a sub 1 times 1/2 to the 3rd power, or 1/8. So 0.075 equals a sub 1 times 1/8, or a sub 1 over 8. Now I can multiply both sides by 8, so I'll do that in the calculator, 0.075 times 8, and that gives me a decimal of 0.6. So a sub 1 would be either 0.6, or if you wanted to write that as a fraction, 3/5. So, like we did with arithmetic sequences, we did the same concept with arithmetic sequences. You can take two terms and put those two terms into an nth term equation to give you a system of equations where you can solve for one of those two variables and then substitute to solve for the other two variables. So if you wrote this as 0.5 and 0.6, that would definitely be okay. We could check this again. So here's my first term, 3/5. And I'm going to multiply that by 1/2, or which would be the same as dividing by 2. This would be the second term. Divide by 2. This is the third term. Divide by 2. This is the fourth term. It matches up with what we have for the fourth term. Divide by 2. There's my fifth term. Divide by 2 again. There's my sixth term. And divide by 2 one more time. And there's my seventh term. So this matches up with the seventh term. So you do have the ability to check these after you find the first term in the ratio by going back and finding all those terms to see if they match. You don't have to, but you have that ability. So these are the different ways that we can use the nth term formula for a geometric sequence. Now there's another formula for geometric sequences, like we saw with arithmetic sequences. We have the ability to find a shortcut for partial sums. So with arithmetic sequences, we found that if you needed to add the first three terms, not a big deal. You can find the first term, add it to finding the second term, and then add that to finding the third term. But if I want to find the sum for the first 30 terms, that could be pretty tedious. Find each of the 30 terms and then add all those together. So instead, we have this formula. Now, this formula is quite a bit different than what we saw with arithmetic sequences, but it does use our common language here. So the CS, remember this capital S stands for series. So a series is adding the nth number of terms. So if I want to find a series, I take the first term and multiply by the quantity of 1 minus the ratio to the nth power. Then divide that by 1 minus the ratio, the common ratio. So this is a little bit of work here, but it can be a pretty quick substitution. So in problem number 7, it says, for each of the following, find the indicated partial sum. So we're trying to find partial sum for terms 1 through 8 in A. So we can substitute in A sub 1 because they tell us A sub 1. It's 2. We can substitute in the ratio. So this would be 2 times the quantity 1 minus. Now make sure that you put, if the ratio is negative, we put that in parentheses. The negative has to be in parentheses because we are taking that value to a power. So in this case, we're taking it to the 8th power because n is 8. And then closing those parentheses. And then all of this is over 1 minus negative 3. So we do have to be careful and make sure we put this negative 3 here in parentheses because this power is going to affect whether that value is truly positive or negative when evaluated. So I'm going to use my calculator to simplify the expression. You could, if you feel comfortable, you can type this all in one string. I'm going to simplify here in parentheses first. So 1 minus, and then negative 3 to the 8th power. And so this simplifies to 2 times negative 6,560 all over 1 minus the negative 3. So if you needed your calculator there, you could, but notice that this is the same as 1 plus 3, which is 4. So now I can simplify this by taking this negative 6,560 times 2, which we have in the numerator, and then divided by 4. And so this is the value. So what this is, this 3,280, this value is what we would get if I took the first term 2 and then added that to the next term, which would be negative 6 because you multiply 2 times negative 3, and then added that to the next term and continued all the way up to 8. It just gives us a shorter method of finding the first 8 terms and then adding them all together. Take a look at B. B is similar, but it's presented to us in a little bit of a different format. So in this case, I is the variable. Notice this is not imaginary. This is the variable I. You don't see this notation a ton, but it happens. So we're trying to find the sigma means sum of the terms from 1 to 9. So we're basically finding S sub 9 here. So A sub 1, it doesn't tell us what A sub 1 is. But remember, this expression here, 3 to the I power, is how we find the value of each term. So the first term would be 3 to the first power. 3 to the first power should be easier for us to find. It's just 3. Then we would have 1 minus r. Now the ratio, it doesn't outright tell us the ratio, but notice that this is 3 to a power. So the first term would be 3 to the first power. And the second term would be 3 to the second power, or 3 times 3. Then the third term would be 3 to the third power, or 3 times 3 times 3. Fourth term would be 3 to the fourth power, 3 times 3 times 3 times 3, and so on and so forth. So what we can see here by this notation, what this means is that we're multiplying each term by 3. So the list would go 1, 3, or sorry, not 1. The list would go 3, 9, 27, and so on. Okay, so we're multiplying each term by 3, so the ratio is a positive 3. Don't really need this in parentheses here because it's not negative, it's positive, but if you put it in parentheses, that's okay. My n value we listed here, so I'm going to substitute in 9 for n, and then this is all over 1 minus the ratio, which we said was 3. So I'm going to do a little bit of simplification in my calculator first, so 1 minus 3 to the 9th power. Ooh, that's a pretty big number, but that's okay. Equals, so this would now be 3 times negative 19,682 all over 1 minus 3, which is negative 2. So then I would take this expression, multiply it by 3, and divide it by negative 2. And there we have the sum of the first 9 terms. The sum of the first 9 terms would be 29,523. Notice that these numbers are probably a little bit larger than anything we encountered in the last target. Because remember, the terms are going to increase or decrease at generally a much faster rate than what we saw with arithmetic sequences, as long as we're multiplying by a number greater than 1. So remember, each term is being multiplied, so those terms can grow pretty rapidly here if we're multiplying by 3 or multiplying by negative 3. So they can grow pretty rapidly in terms of their distance from 0. let's go ahead and take a look at C. If you're feeling pretty comfortable with this formula, go ahead and pause the video and see if you can find the answer to C. Find the series for the first 7 terms in C. Okay, hopefully you had enough time there and you got an answer. Now let's go ahead and take a look at this answer. So I put the equation up here, the series equation or the partial sum for a geometric sequence up here on the screen. We do need to make sure that this is a geometric series or sequence here. Sorry, sequence or series. So if we're going from 4 to negative 12, notice this negative goes with the constant 12. So if I'm going from 4 to negative 12, to multiply to 4 to get to negative 12, I'd have to multiply by negative 3. And again, this is multiplying. We believe this is geometric. Then if I had to multiply from negative 12 to get to 36, I would multiply by negative 3, and this works. So we know that the ratio here, we can see that the ratio here is negative 3. So if I want to find S7, the sum of the first 7 terms, they gave us 3 of them, but not all of them. You could find the other 4 and add them together, or we could use this formula. So the first term is 4. So I'd have in the numerator 4 times the quantity 1 minus negative 3, again, does have to go in parentheses, to the 7th power. So the n in this case is the first 7 terms. I take it to the 7th power. This would be over 1 minus negative 3. So if I simplify this expression, I would take, again, you can put it all in your calculator one time if you like, but if I simplify this expression in the numerator, 1 minus negative 3 to the 7th. We've got to make sure we put that negative 3 in parentheses, so it's taking the 7th power of the negative value as well. This would be 4 times 2,188 over 4. And so we could type this in, but we could also notice that the 4's would cancel out, and so the sum for this would be 2,188. So if I added the first 7 terms, that's what I'd come up with. Let's go ahead and check this by doing this by hand. So 4 plus a negative 12, or 4 minus 12, plus 36, that's 3 terms. So then the next value would be 36. Let's not check it, but you could. I won't waste your time doing that. But if you did find all 7 terms, you could add all 7 terms together, or you can use this equation. Okay, so these are the 2 equations that we're going to have for geometric sequences. Again, we saw both of those style of equations for arithmetic sequences. They're just slightly different to account for the differences in the way the sequences are set up. Let's go ahead and take a look at an application problem. So in problem 8, it says a pendulum is any object attached to a fixed point and allowed to swing freely. There's a typo there, but I'll have that fixed for your notes. Freely under the influence of gravity. Suppose each swing is 0.9 the length of the previous swing. Gradually, the path of the object will become shorter and shorter, and at some point, the pendulum will appear to have stopped. So basically what we have, if you're uncertain what a pendulum is, you may have seen these in clocks before on different apparatuses. Say we have something that's attached to a string and it's attached to some, I don't know, some fixed point here. And we take it and we pull it back in this direction along an arc. Then it'll swing all the way through to create an arc path. And then it will go back through and it will keep going back and forth, eventually reducing the distance that it travels in this arc pattern. Okay, we could go back to geometry and talk about arc length, but we're not gonna do that here. It gives us the arc length. We don't have to find it. So what it does tell us is that each time that it swings along that arc pattern, so it swings that full distance and then it comes back, but it doesn't always make it exactly to the end, and then it comes back and it doesn't make it exactly to the end, and it's reducing that distance. So it does tell us that this distance is being reduced. It's 0.9 the length that's before. So basically what this is the ratio. So if it first travels, let's say, I don't know, let's say it travels 100 feet. Then the second time it's going to travel 90 feet. And then the next time it's going to travel 810 feet. And then the next time it's going to travel 720 feet. That'd be a very large pendulum, but you get the idea. So this is the ratio. Part A says, how far does the pendulum travel on its 8th swing if the first swing was 2 meters. So I have both of the two equations we have up here for geometric sequences. This one wants to know a specific value in the sequence, the value of the eighth term. So I'm going to go ahead and we're going to use this equation on the left, the nth term for a geometric sequence. We are going to be finding a sub 8. So what we need to know is what was the length of the first swing, a sub 1? Well, it tells us right here that it was 2 meters. So this is a sub 1. We're going to put that in. What is the ratio? Well, the ratio is 0.9 or 9 over 10. We can use the decimal, that's okay, zero point 0.9. We would be taking the ratio to the n minus 1 power, so this would be the 8 minus 1 power, which would be 2 times 0.9 to the 7th power. And so if we need to round here, we can. It doesn't tell us to round, but in word problems, we're generally going to round instead of putting them into fractions. Gives us a better sense of what that value means if we're not going to use it again. And so on the eighth swing, it's going to, if we calculate this out, it's going to travel approximately 0.9, let's round to 2 decimals, 0.96 meters on the eighth swing. So we can find the distance that it travels on any given swing using this nth term formula for a geometric sequence. So it initially started at 2 meters. After the eighth time that it passes through in a swing, it's going to be a little under 1/2 of that distance. Now, B says, what is the total distance traveled by the pendulum for those 8 swings? So remember, it's going back and forth, back and forth, back and forth. So if I were to find, it's kind of hard to see here, but if I were to find that distance that I just traced there, that would be the total distance that the pendulum traveled. So in order to use that, if we're trying to total, we want the partial sum formula. So in this case, we are trying to find S sub 8 because it is 8 swings that we're dealing with. So we do need to know a sub 1 here in the formula. A sub 1 is 2. It gave us that information on the previous problem. Then in parentheses, we would have 1 minus the ratio, which the ratio again is 0.9 to the nth power. The nth power, if it's going to go through 8 swings, would be 8. All over 1 minus 0.9. If I simplify this equation, or this expression, I'm going to go ahead and do part of the numerator in my calculator. So 1 minus 0.9 to the 8th. Well, that gives me a pretty drastic number there. Let's see if I can put it in a fraction. I cannot, so I'm going to go ahead and type all of this into the calculator then in one foul swoop. So I don't. You could rewrite that number if you wanted to. I don't feel like rewriting it, so I'm going to do 2 times 1 minus 0.9 to the 8th power. Close my parentheses, then divide by, and then I'm going to put my denominator in parentheses as well. Be careful there. Divide by 1 minus 0.9, and this is going to give me a total value here. So this total value is going to be approximately, again, let's go ahead and round to 2 decimals, approximately 11.39 meters traveled through 8 swings. So in this case, we wanted to know a total distance, the sum of how far it traveled on the first swing by the sum of how far it traveled on the second one, and so on and so forth through the 8th swing and add all those together. And we can do that using the partial sum formula. Now finally, the last question says, how many swings until the length of each swing falls below 0.5 meters, below half a meter? So in this instance, it doesn't tell us what we're finding, how many swings we're looking for. We're trying to figure out what's the number of swings. So basically, we're trying to find for n. It's giving us some information. This information is that the length of a single swing is needs to be below zero point 0.5 meters or 1/2 meter. So it's not a sum. We're not going to use the equation on the left. It is the length of a single swing. So we're going to use the nth formula, which I'm going to bring down. So what I know here is that a sub n is the length of the swing, 0.5 or 1/2. You can put in either or. 1/2 has to be less than the length of the length of the swing has to be less than 1/2. So a sub 1 is going to be, I'm going to use a less than symbol. If you use equal here and then eventually convert to understanding the concept of it, that's fine, but I'll just use a less than symbol. A sub 1 is still 2. The ratio is still 0.9. And then this is going to be to the n minus 1 power. So to solve this, first I would divide both sides by 2. So if you do this in the calculator, 0.5 or 1/2 divided by 2 would give you 0.25 or 1/4. So 1/4 is less than 0.9 to the n minus 1 power. Now, how do I get rid of this exponential equation or get the exponent out of the or get the variable out of the exponent? I have to use a log base 0.9. And again, you can write 1/4 as 0.25 or 1/4, but I would take a log base 0.9 of both sides of the equation. What that would do, would the log base 0.9 and the exponential base 0.9 would eliminate each other, so the left side of the equation would read log base 0.9 of 1/4 or 0.25 is less than n minus 1. Now I can add 1 to both sides. So n has to be greater than 1 plus log 0.9 to the 1/4 or to the 0.25 power. So remember to put that in, I can type in 1 plus log of, using the change of base formula, log of 1/4 divided by log of 0.9 or 9/10 if you put that in a fraction. And there we have it. N has to be greater than about 14.16. So how many swings will it take for the distance of that swing to be less than 1/2 meter? It's going to take over 14.5, so it's going to take 15 swings. So here we want to define the length of a single swing, or how many swings it's going to take for the length of a single swing to be less than 1/2. So we use the nth term formula, but this time solving for n. And this is the conclusion of target SS3. Okay, so hopefully you took good detailed notes throughout that video. Remember that you will be able to use these notes when it comes time to taking our online assessment at the end of the week. For the rest of this week until Thursday, you guys should be working on the homework assignment. That is IXL for school level guys. For my honors guys, that homework assignment is posted on Google Classroom. See if you can complete those questions and compare with the answer keys that are provided individually. If you run into questions, make sure you write those questions down or shoot me an email. On Thursday, we will go over the questions that we have in preparation for our online assessment on Friday. Thank you guys for tuning in. Have a good day.